We'll see more on vector field and flow line. Vector field and flow line. This is what we are talking about. So, a vector field is a kind of a function. If we pass a point xy, then it generates a vector at x comma y. That is the vector field. So if I have a function, algebraic function, if I pass x comma y, then it gives us a value that can be a vertical value or density in the xy plane. This is what we have seen. But if we have, instead of algebraic function, if we have a vector field, or rather we can say vector function, then if we specify x comma y, then it gives us a vector rather than a value. So it is a vector factory vector function. Algebraic function is denoted by small f, whereas vector field is denoted by capital F. Capital F, and then on top of it one arrow sign. It denotes that it has to do with a vector. It is also a vector. So we can say that if I have a vector, then vector can be a static vector in the sense that x component, y component, z component, or its orthogonal components are static value or scalar. Whereas if we see the kind of vector field, it is also has x component, y component, z component. If I have a static vector, it has x component, y component, z component, or any set of orthogonal components, and the value of the orthogonal components are scalar, whereas vector field also has orthogonal components where orthogonal components each value is again a function over x, y, z. So if I say capital F is vector function, then x comma y comma z, or xt, yt, zt, if that is the dependent variable, then it can be further disintegrated into f1, f2, f3, f4. However, is the orthogonal component. So f equal to f1, f2, f3, where f1 is f1i, f2 is f2j, f3 is f3k. So if f is a function over x, y, z, if we see from the algebraic side, or if we see from the parametric vector side, then f is a function over xt, yt, zt, where xt, yt, zt are components in the parametric vector where the independent variable is t and dependent variable are the components x, y, z. So f, capital F, xt, yt, zt equal to f1i plus f2j plus f3k, where f1 is again function over x, y, z, or xt, yt, zt. Similarly, f2, f3, and so on. So this is what we have seen, the vector field. Now, if vector field, generally what we consider is a kind of a velocity field. If it is a velocity field, then it is a differentiation or derivative on top of on top of algebraic equation. So if this is algebraic equation and this is vector field and this is algebraic equation and this is vector field and this is parametric vector, then algebraic equation, parametric vector, they lie in a same line. If that is true, and if this vector field is differentiation derivative of algebraic equation, then this is derivative of parametric equation also. So if I calculate antiderivative of vector field, then we get the flow line or the parametric vector. So this is what we are talking. So in a sense that if I have, suppose that if I have a very small paper or plastic, that is if I drop on a stream, water stream has a velocity, then it moves along the water stream. So if that is true, then if I know the velocity of the water stream, then I can calculate at what point at what time, what would be the displacement of the paper strip from the origin where I started calculating the time. But if I have, in a sense that if I have a vector field, Okay, if I have a vector field of the water flow or something like that, then at each moment it can give the direction also. Or if I have a magnetic field, then if I take the path of the compass needle what we placing along the south pole and north pole of the magnet, then each point the needle direction would be different. So vector field is more on the algebraic equation, where if I integrate the velocity, then I get the displacement. But if I integrate the velocity vector, then I get the kind of displacement vector. Okay. So if I have a kind of velocity equation in algebra, if I integrate it, I get back the different distance vector, distance algebra. If algebra represent velocity, if I integrate, then I get the distance algebra. If I have distance algebra, if I differentiate, I get the velocity algebra. If I have velocity vector, okay, algebraic equation in the sense that it has ijk component and each component is algebraic in algebraic form. If that is true, then if I integrate it, I try to calculate the distance vector, that is also called flow line, or the kind of parametric vector, then it gives the flow line in terms of vector 1. So vector equation, it leads in vector 1. Okay, so now what can be various use of it? Let's suppose I have, let's suppose that I have a kind of one equation. Okay, I have equation like fxy, algebraic equation, fxy equal to x square plus y square. Fxy equal to x square plus y square. If that is true, and if I consider fxy as vertical value, not the density function, then z equal to x square plus y square. If x and y are 0, then z is 0. So if this is x axis and this is y axis, if this is x axis and this is y axis, then this is origin. If this is the origin, at origin z is also 0. But as we grow along x and y, then z grows in a kind of power fashion, square fashion. So if x is 2 and y is 2, then z is 4 plus 4, that is 8. If x is f if fx is 8 and y is 8, then it is 64 plus 64. So it grows like a square fashion. So it makes a paraboloid. So in y direction, paraboloid, in x direction, paraboloid. So altogether, it is a paraboloid. Okay. So if it is a paraboloid altogether, if it is a paraboloid, then what is the vector field? If the equation is fxy equal to x square plus y square, what is the vector field? I can differentiate and I can get the vector field along x-axis and vector field along y-axis. So 2xi plus 2yj, that is the vector field. So capital F braces x comma y is 2xi plus 2yj. If that is true, then what is it? So this is gradient. So this is called gradient vector. So gradient vector is nothing but it's a vector field. If gradient vector is vector field, then xi 2xi plus 2yj is a vector field. How we can kind of draw in a space about the vector field. Suppose that I am taking a paper. I have a paper. On the paper, I am drawing contours. So suppose I have a kind of a hill, or I have a surface that is elevated. So surface can be at some time the slope is less. So like this is the slope. So initially slope is like this. If I move more along the x-axis and y-axis, the Z would grow little, but after some time it is like this. So if I grow less in X but Z grow high, if I draw the contour, the initially contour will be far distant. If I take a kind of X and Y in the contour diagram at equidistance, then contour will be far away. But when slope grows, then okay, so if I take, so now instead of saying that if I take equidistance x, if I say equidistance in the contour, so contour of 2 meter height, contour of 4 meter height, contour of 6 meter height, if I take this kind of circle on a paper, then distance will be high between them because at far distance we have the contour. But when the whatever slope surface we are taking 3D surface, if it grows like this, if it grows like this, then the contour what we are getting as 3 meter high or 6 meter high, suddenly 9 meter high will be packed up. So in a small region, we'll get 9 meter high, 12 meter high, 15 meter high, 18 meter high. So it will be packed where slope is high. If again it becomes flatter, then again it will be far distant. So if I see 2xi plus 2yj, then if I draw the diagram, then it will be perpendicular to the contour. If I draw the vector, so suppose this is the xy plane. Okay, so this is the xy plane. If this is the xy plane and these are the contours, contour, then contour, then contour, then 2x plus 2y, the direction would be like this 45 degree, then like this, then like this. Everywhere it will be like this. It shows that if this is the contour, then it is perpendicular to the contour. Okay, if contour is circular, then everywhere x, y that is at 45 degree or x and y are kind of for x 2x plus 2y. So the slope in x direction and slope in y direction dz by dx and dz by dy are same. So if I draw, then it will be like this. Here it will be like this. 2x plus 2y means along the x-axis contour will be like this. Along the y-axis contour will be like this. Along other as per the xy. Okay. So if I have contour like circle, then everywhere the kind of gradient vector is perpendicular to the contour. So the gradient vector is the gradient vector is always perpendicular to the contour. Okay, so if I kind of see the kind of paraboloid, so we'll see how the paraboloid looks. Then we will move on. Okay, so this can be kind of typical case of paraboloid. So this is paraboloid. So at the kind of center, at the kind of center, it is like it is origin and it moves like this. This is typical case of paraboloid, but it will not converge here. It will go like this only. So this is typical example of paraboloid. So the equation what okay. So the equation what we have taken that fxy equal to x square plus y square then 2x plus 2y. If I draw the contour, then it will be as we said that it will be if I draw the contour, then it will be if this is the contour, then it will be perpendicular to the contour everywhere. So if I say the kind of the x square plus y square if I get the vector field, that is 2xi plus 2yj, then this somewhere will say this is gradient vector. So vector field is gradient vector is nothing but it's a vector field only, because if I set x, y any value, it will generate a vector. So if I have x equal to 3 and y equal to 0, then it is 3i. If x equal to 0 and y equal to 3, then it is 3j. If x equal to 2 and y equal to 3, then it is 2i plus 3j. Everywhere it is perpendicular to the to the contour. That is one idea. But if contours are nearly placed, okay, so if one is here, next is here, then next is here, but after that within this much distance I have 20 contours. So within this much distance I have 20 contours, and within this much distance I have 3 contours. So here the it will be perpendicular to the contour, but it will be have sharp rise as far as gradient vector is concerned. How? It looks like this. Okay. So suppose this is the hill. So this is origin. From origin, hill is like this. So we draw the contour, and contour, if I see the equally spaced contour, means equally height contour, then they will be far distant. But from here, it goes like this. Now here, if I have x component and y component, x component, y component and z component, with little variation in x and y, the z variation is sharp, high. So if I increase 1 in x, 1 in y, probably there is 100 increment in z. Okay, if that is true, if there is 100 increment in z, whereas at the beginning, if I increase here 10 and y 10, z may increase 0.5 only. So if the kind of gradient vector is perpendicular to the contour, then here it will be perpendicular to contour. Means if I drawing the contour, it is perpendicular to contour, but it will see the rise the way the function is, the algebraic function is growing. So we can say that gradient vector is perpendicular to the contour, but direction will be along the fastest growth in the function. So if function is like this, then growth is less. Where the function is like this, then the way fastest growth is happening, in that direction gradient would also go up, because z vector is increasing more in comparison to the x and y. So that is the scenario. Okay, so this is kind of a story of the gradient. We will talk more about gradient when we'll talk more about the parameterized vector. But this is what generally people talk as far as gradient is concerned. Okay, I believe it will take a lot of time. Anyway, so this is the situation of the vector field and gradient. So we are in the context of vector field and gradient. So if I have an algebraic equation and if I differentiate it along x-axis and y-axis, it gives me gradient vector, but it gives me vector field also. Means gradient vector looks like a vector field. If it is 2xi plus 2yj, then if I keep changing x and y, it keeps giving me different vector. It looks like a vector factory. So it is a vector field. So gradient vector is one of the good example of vector field, where the gradient vector direction is perpendicular to the contour what we draw, and it moves sharp in the direction of the when the vertical grows in that direction. So that is kind of story of the vector field. Now if I want to calculate the flow line in the sense at each moment what is the distance, like a person is walking with a velocity, then if I multiply the velocity into the time, then it gives me the displacement. But if velocity is an algebraic equation, then I have to do the integration. Rather than calculating the multiplication, I'll do the integration. then again it gives me distance. So if I put the variation in x, then at each time variation in t, then at each time what if I put the variation in t and velocity varies, that is acceleration. But if I calculate, if I integrate with t, then whatever the function we get as a function of t, if I keep changing the t from the beginning, I keep getting the distance. Like that, dash distance is called flow line here in vector field. So if I vector field denotes a velocity, and if I integrate the vector field, then I get the displacement vector or flow line. But if vector field has x component, y component, z component, then flow line will also have x component, y component, and z component. Then flow line is also a vector. So that is the scenario. Now, if capital F equal to F1, F2, F3, or capital F equal to F1i plus F2j plus F3k, then and F is derivative of a flow line of parametric equation, then dr by dt equal to F. If dr is xt plus xti plus ytj plus ztk, then dxt by dti plus dyt by dtj plus dzt by dtk equal to f1i plus f2i plus f3j. If that is true, then dxt by dt equal to f1, dyt by dt equal to f2, and dzt by dt equal to f3. Okay, if that is the case, then xt equal to integration of f1 with dt, and like that. So yt equal to integration of f2 with dt, and zt is integration of f3 over dt. So that is kind of getting the flow line. So if it is 2x and 2y, 2x and 2y, then what is the integration of 2x dt, 2y dt, and 2y dt? 2x dt and 2y dt, they are two components of the flow line. We cannot tell. Not possible. If it is kind of, if I have equation like integration of integration of dt and integration of x dt, if x component of the vector field is 1 and y component of vector field is x, suppose, then 1 dt is t plus x0. Now that I can substitute there, then it will become t square plus tx0 plus y0, where x0, y0 is a point through which it is passing. Okay, so that is the scenario. But if it is, if I have x dt and y dt, so we cannot integrate, not possible. Okay, otherwise, if it is a kind of y dt and there minus x dt, then it can be sine and cos, because integration or differentiation of sine would result in cos. So if I have a vector field where I have each f1, f2, they are function of x and y, blindly we cannot integrate with dt, not possible. Okay, then how I can get the flow line? So flow line points at each time at each t that we can calculate. So this is called Euler method. Euler method of calculating the flow line when the vector field is in function of xy. So if one of them is constant, if suppose that vector field is xi, vector field is yi plus plus 1j, then if I integrate 1j, then it results in t, 1j, 1 dt t. Now y component is t plus y0. I can place here, that is x is y is now t plus y0, so t square by 2 ty0 plus x0. But one has to be constant. Then only we can proceed with the integration. But if both are variable in x or y, then integration with t is not possible. So Euler method says that if I have a vector called rt at any time and in any t,